Our next speaker is Katie Dagon, I hope I'm pronouncing that right, from the National Center for Atmospheric Research. We'll be looking at precipitation extremes. Take it away.
Thanks so much. Hope you can see that okay, just give me a shout if not. So yeah, thanks to the organizers for the invitation to speak. My name is Katie Dagon. I'm at the National Center for Atmospheric Research, and I'm going to talk about some work where we've been leveraging machine learning-based feature detection algorithms to identify synoptic weather events, but also to then associate those detected features with extreme precipitation. And this work is in part funded by the Department of Energy through a cooperative agreement at NCAR called Catalyst. So the motivation here is that we know that extreme precipitation has significant consequences. I'm showing some examples from a couple of years ago, but we've already seen many examples this year. I think someone in the morning session mentioned the extreme flooding that we've seen so far this year. But we also know that extreme precipitation comes from many different sources. So I'm showing on the right an example of some of the flooding after Hurricane Harvey, so tropical cyclone, extreme precipitation. But then on the left, I'm showing an example of the Oroville Dam spillway overflowing a couple years ago after an atmospheric river event. And if you're not familiar, atmospheric rivers are sort of these long bands of moisture that sort of transport moisture and precipitation from the tropics to the mid-latitudes. So we'd like to be able to better understand and distinguish different sources of extreme precipitation, and also think about how the mechanisms for them might change with climate change. So as I mentioned, we're going to leverage some of the work on machine learning for pattern classification or feature detection that's sort of been well developed over the years. And so some of the particular goals of this project are to apply and develop different machine learning based detection algorithms to automate the classification of synoptic weather features such as atmospheric rivers, tropical cyclones, and fronts. And I'll spend the first part of the talk talking about atmospheric rivers and tropical cyclones. And then the second sort of longer part, we'll talk about the frontal detection work that we've been doing. But then also kind of bringing it back to the motivation, studying the causes of extreme precipitation by associating those features with extreme precipitation events. And because this is KGML, I'm going to try and sort of highlight examples where we utilize a knowledge-guided approach to machine learning for this work. So to start with the detection of atmospheric rivers and tropical cyclones, we're leveraging an existing project called ClimateNet, which is based at Lawrence Berkeley National Lab. And we're collaborating with Karthik Kashnas and Arvind Nayak on this work. And so what they've done here is created this really unique community-sourced, expert-labeled data set to detect atmospheric rivers and tropical cyclones. So what I mean by that is they've actually gotten experts to hand label from climate model output tropical cyclones and atmospheric rivers in order to build a training data set for a machine learning detection algorithm that can be then used in an inference state to detect these features in other data sets. And so if you're interested in the sort of nitty-gritty details of the machine learning model, I would refer to you to this recent paper, Prabhat et al., which talks a lot more detail about the training and the architecture. But I do want to just mention the sort of uniqueness about this data set in that it is based on expert labels. And there were several sort of labeling campaigns that they held within the past couple of years. We held one at NCAR back when we were in person in 2019. And so this animation is kind of going through how these expert labels are collected. So the tool samples a random time point from climate model output, because again, that sort of serves as the baseline information for the training data. But the user can toggle between different output fields, for example, water vapor, pressure, winds, whatever knowledge or information is most useful to categorizing these events. And then the expert actually goes in and draws boundaries, like the animation is showing, around a particular event, labels it as either an atmospheric river or a tropical cyclone. And then kind of interestingly, I think from an uncertainty quantification perspective, is also able to add their confidence level in terms of whether they are sort of low, medium, or high confident in the classification of a particular event and also the bounds of that event. So our question was kind of seeing how we could leverage this existing trained model and use some of the simulations that we have at NCAR. So in particular, community Earth system model, which has already been mentioned a couple of times, CESM simulations that were run at high spatial and temporal resolution. And the high temporal resolution is really key for capturing these dynamic features. But the question was, can we use the pre-trained algorithm applied to climate model output and still detect these features? And so this animation is showing that we've been able to have success with that. So here I'm showing labeled atmospheric rivers in red and tropical cyclones in green. And this is from the CESM model output run through the trained algorithm. And if you're interested in the particular fields, I'll talk about this a little bit on the next few slides. It's using vertically integrated precipitable water, sea level pressure, and UV winds at 850 millibars. And so then it outputs either sort of a classification label spatially for atmospheric rivers, tropical cyclones, or none. There's a couple interesting things to point out here that will lead me to the next slide to talk more about atmospheric rivers, but you'll notice there's a tropical cyclone feature here that as it evolves over time kind of seems to morph into an atmospheric river. And so that's kind of an interesting question where we might be able to look more into the genesis of atmospheric rivers and how they form and how they evolve. But in particular, because we're able to detect these atmospheric rivers, we wanted to bring in some knowledge from another related project, which my colleague Christine Shields at NCAR is one of the leads on, and that's the ARTMET project, or the Atmospheric River Tracking Method Intercomparison project. And so this is a project that is trying to understand the differences in atmospheric river science based on detection algorithms. And so this plot on the right, I'm showing from a recent paper comparing many different atmospheric river detection algorithms. And they were developed for slightly different purposes. So it's not all that surprising that they sort of vary in their sort of spatial extent or definition of an atmospheric river. But what's interesting from our perspective is that many of these detection algorithms are based solely on, often solely on a single input field. So integrated water vapor transport, or IVT, shown here. While the detection methods might vary in other ways, for example, using absolute versus relative thresholds, a lot of them are just based on IVT. And so with this sort of information in mind, we wanted to go back to our detection that was trained on 4 input fields and sort of ask the question, do the results change when altering the input fields? And so in fact, when we repeat the training for a single input field, just the vertically integrated precipitable water, we're still able to detect ARs. We're not able to detect TCs, but we're still able to detect the atmospheric rivers with similar spatiotemporal representation as the model trained on all 4 input fields. And I want to just give John Truesdale a shout out for his help retraining the algorithm here. So that's kind of a nice example of using the machine learning in a knowledge guided approach. It's also a nice example of transfer learning because we're able to apply these pre-trained algorithms to different climate model data sets and also to kind of mix up the input fields and see sort of what the results look like. So that's all I'm going to say about the atmospheric rivers and tropical cyclones. I want to spend the rest of the talk talking about a different detection algorithm, which was designed to detect different front types. And so for this work, we're collaborating with Jim Baird and Ken Kunkel at NC State. And they developed an algorithm called DL front, which is based on detecting different front types. And the input fields are a little bit different here. So they're looking at surface fields, surface temperature, sea level pressure, specific humidity, and surface winds. And then actually outputting 4 different frontal categories, so cold, warm, occluded, and stationary, as well as the none sort of background type. And in their paper, which has a lot more details on the type of the machine learning algorithm and the architecture and things like that, but they are able to successfully detect about 90% of manually labeled fronts over North America. A couple of things to note here: the spatial domain is now just North America, versus what I was showing with ClimateNet, which was a global spatial domain. And the reason for that is really based on the training data set. So again, kind of one of the challenges with these sort of detection algorithms is where you're getting your training data. And so for this front detection, they were able to leverage a human labeled data set from the National Weather Service that I'll talk more about on the next few slides. But it was limited spatially to North America. So hence the reason for the change in spatial domain, but again, sort of importantly, able to use those human labels of fronts to be able to validate the performance of the front detection. And so our question was, again, can we use this pre-trained algorithm applied to our CESM output to detect weather fronts? And again, we're able to do that, and we're able to distinguish between the different front types in the CESM output. But I wanted to kind of take this a step further and sort of ask the question, how do we validate these results coming out of CESM? How do we know that the detected fronts actually make sense in terms of real world perspective? And I mentioned earlier that we have this human labeled data set. It's called the National Weather Service Coded Surface Bulletin, or CSB. But now that we're sort of comparing a human labeled front data set to climate model output, it's less useful to just look at a random time point and compare the front locations, because we wouldn't expect the climate model atmosphere to perfectly represent the real world at that particular time point. These are fully coupled climate model simulations. So what we can do, though, is we can look at statistics over time and sort of compare the detected fronts in the two different products on sort of a larger scale. And so that's what I'm showing here. I'm going to show a couple of slides that look at seasonal front rate crossing climatologies. And so what I mean by that, sort of looking at how often fronts pass across the North American spatial domain. And so calculating a sort of spatial mean front crossings per week, and then looking at that seasonally. And so we're comparing the climate model results from CESM in orange with the validation data from the Coded Surface Bulletin in blue. And so we can see that there's pretty good agreement across all of the available years that we had, which was limited by the CSB data set. So pretty good agreement across the different seasons, well within the standard deviations for those two data sets. We can also look at this spatially. So again, this is kind of taking a step back and not doing a spatial average, but looking at the contiguous United States and just comparing the spatial patterns, which again look pretty good. I should note here that I've combined all the front types into just all or none, but we can also look at that sort of breakdown by front type. As I mentioned before, the detection algorithm is able to distinguish between the different front types. And so if we do that, we see that there's slightly less good agreement for the warm fronts and the occluded fronts, though these are overall less frequent if you sort of compare the y-axes for these different plots, whereas the sort of total front crossing climatologies are more dominated by the cold fronts and the stationary fronts, which do show very good agreement, mostly within the standard deviation across the models and the observations. But we wanted to go a step further, do some further validation of the CESM output. One of the reasons for this was that we had to kind of adjust the input fields that we were using from CESM, purely based on the fact that some of these high resolution simulations do not have all the input fields saved at 3 hourly temporal resolution, which is what we need to run through the detector. So what we did was we also wanted to compare to some reanalysis data where we did more apples to apples comparison, and we tried to use the same input fields from MERA and from CESM. The difference here is that they're both run through the front detection algorithm. So unlike the previous comparison where we had sort of a ground truth observations with the climate model, machine learning detected fronts, these are both products that are run through the machine learning algorithm, but it can still give us some sort of more insight into the skill of the front detection. And it's really a more feasible alternative than having to go and hand label fronts in CESM itself. So again, we're showing good agreement for sort of a 16-year climatology that I've pulled from MERA reanalysis and CESM. If we look spatially, we continue to see some good spatial agreement in terms of the peak of the magnitude is sort of in the central US. Perhaps CESM may be slightly underestimating the front detection in sort of that sort of peak magnitude relative to MERA. But in general, we're seeing pretty good agreement. So given that we have done all this validation and we feel pretty confident in the detection, we can then sort of move to comparing the front detection response for two different climate states. So here I'm showing both CESM, two different simulations with a present day climate and a future climate with RCP 8.5 foreseen at the end of the century, and comparing the climatologies again. And we were surprised to see that they're actually pretty similar. Looks like maybe there could be a drop in JJA that I'll talk about more in a little bit, but overall not seeing very significant differences, at least for this particular metric of sort of spatially averaged front crossing rate climatologies. Again, if we look spatially, we do see some differences in the spatial patterns with season. And it does seem like there could be a decrease or potentially northern shift in JJA with climate change that I want to dig into a little bit more. So I'm going to show you instead the difference plots, which just makes it a little bit easier to compare the plots on the previous slide. And again, it does look like JJA shows a decrease in the detected fronts, more so than some of the other seasons where you see kind of a mixed response spatially in Northern Hemisphere winter and spring, and then less of a response in the fall. So again, I want to kind of bring in some knowledge guided approach here. We were thinking of possible mechanisms responsible for a decrease in detected fronts with climate change in the summer. And so we actually were thinking about the response of the jet to climate change. And so I'm showing here actually some work from one of the workshop organizers, Libby Barnes and Screen 2015, looked at the jet latitude response of the North Atlantic jet shift under climate change. So these are from CMIT models looking at the response to RCP 8.5, future climate response, and looking at that with by season, by month. So what you can see is, while the response is a lot less certain in winter, and this is still a very active area of research, it does indicate that there could be a northward shift of the jet in the summer, and that could be responsible for this decrease in detected fronts. However, we don't really see that decrease as much in the fall, whereas we might still expect to see a shift in jet latitude. So this is something that we need to dig into a bit more, and also to try and test this response in other climate models and other CMIT models, and see if the climate change response is consistent. So in the last couple of minutes, I want to bring it back to the beginning and talk about how we actually connect these detected features to extreme precipitation. And so here I'm just showing a snapshot at a particular time point of 90th percentile precipitation from the climate model and the detected fronts. So basically what you can see is there are some places where the extreme precipitation lines up with the detected fronts, and then there are some places where it might not, indicating possibly another source. So we wanted to dig into this and quantify this instead of just looking at a particular time point, a random time point. And so I'm going to walk through the sort of steps we took to do that on the next couple of slides. So we started with precipitation output from the climate model. And this is where it's great that we have this large data set of climate model output, because we can actually compare the precipitation from the same time period and the detected fronts. So we start with the precipitation field. We pick out the grid points that are greater than the 90th percentile precipitation for the particular time period. We then compare that to the detected fronts for a particular time point, and sort of ask the question, which of those extreme precipitation grid points are associated with a front? And here I'm just doing it by lining up, which grid points overlap, but there's probably lots of different ways we could look at this. In addition, there's lots of different ways to define extreme precipitation, so that's something we're going to think about as well. But if we sort of look at this sort of snapshot and compare the percentage of grid points that are associated with a front relative to the total extreme precipitation grid points, we can then actually start to look at some large scale statistics. So this is a plot showing the percent of, here PEX means extreme precipitation, percent extreme precipitation grid points associated with the front for the sort of present day CESM simulation. But this is looking across all of those years and taking a climatological monthly mean. So you can see that there's a strong seasonality to that, where it's higher in the winter, lower in the summer. If we look spatially, we can also see some differences where there's certain regions of the US where the precipitation extremes are more dominated by a front. Then we can also compare to the future climate simulation, where we still see that strong seasonality, but possibly a decrease in the precipitation extremes associated with fronts. And I'm going to show you the difference plots to make that a little bit clearer before I wrap up. So this is the difference in seasonality, where you can see it's negative, so it's a decrease in all seasons with RCP 8.5, more so in the winter. And then kind of an interesting dipole response, which we're still trying to sort of dig into spatially in terms of decreases in the eastern US, but maybe some increases in the western US. Now, part of this could be that we saw that there was a decrease in fronts detected with climate change, but we also have to dig into the response of extreme precipitation to climate change. And finally, we'd also like to repeat this analysis for the atmospheric rivers and tropical cyclones in order to understand how those features are responding to climate change. So I think I will end sort of quickly with these few summary points. I know we want to get to questions. I've sort of talked about all these main conclusions, and then just talking briefly about some next steps. I've talked about some of these, checking the response to other models, the resolution dependence, applying explainable AI, which I know is the subject of a lot of the talks here. And I'll just leave it at that. Here's my contact information. Thanks very much for your attention.
All right, thank you very much. We do have a few questions. I'm sure more will come in. The first one is, I'm wondering if the ClimateNet tool is available for the public.
Yeah, there's a link on the slide where I showed about ClimateNet that you can go, and I think it's possible that the tool is still collecting data. I'm not sure, I'd have to check with the the leads of the project, but there's also the paper that I mentioned that sort of reports some of the preliminary results, and hopefully, more papers to come. So I would, I know these slides are going to be posted, so I would just check out that link that I had for the ClimateNet project.
Let's see, the second question is mine, so we'll skip that one for the moment. The other one is, in the DL front model, what's the rationale for using a constant number of filter maps? Why not an expansion type?
Yeah, that's a great question that I don't know the answer to. I would refer you to the publication that I mentioned that really goes into the details of the architecture and why various choices were made. I know it's a CNN architecture, but I'm not familiar on the nitty-gritty details of the architecture. So that's the Byard and Kunkel 2019 paper.
It looks like we've still got a minute, so I'll ask mine. So for the front detection work, were the inputs picked a priori? Did they emerge from the analysis as the best inputs for identifying fronts?
Yeah, I think it was a combination of the two. I think there was some testing done, but once they sort of settled on the surface fields, and again, just what data was available, and that's a challenge we've had applying this to the climate model simulations. Do we have the right output fields available at the right temporal frequency? So we've had to be a little creative, especially with humidity, by swapping in some alternate fields, and also even maybe using 6-hourly data instead of 3-hourly data. But it's kind of a nice test of the skill of the algorithm, that it's able to still detect fronts even when we have to make these sort of substitutions.
Okay, thanks. Maybe time for one more. Do the detection algorithms know the geographic location of the extremes, or is the detection based on relative features that are invariant to translation?
The detection algorithms do not know the locations of the precipitation extremes, except that they're getting, related input fields, I guess I would say, like for the CESM example with the fronts, It's just getting, surface temperature, humidity, winds, and pressure. And so the fact that we sort of independently then look at the precipitation output from CESM, we're able to see some overlap in those features, but the detection algorithm itself isn't seeing precipitation directly.